All right, everyone. This is Noah. I am making a guest appearance because I can't seem to find Greta's video for doing the nth roots of complex numbers. So I'm going to break this into two videos. This first one, we're going to look at our first example, finding the principal square root of 1 plus the square root of 3i. And I'm just going to break this down step by step for you. I'm going to start by just giving this a letter. It's not super important, but square root of 3i. I'm later, I want to say the square root of z equals, yeah? And we know that a complex number written in its standard form, a plus bi, can be written in a polar form as r times e to the theta times I, which is just a fascinating fact that I'm not going to get into right now. I want to focus on the process here. Before I can find the polar form, I need to know the radius and the angle that this makes. I'm going to go ahead and draw a coordinate plane here. I have the real part of the complex number that's on the horizontal axis, and the imaginary part goes on the vertical axis. I'm going to then give myself a scale. We don't need to show a whole lot here. The complex number we're looking at, 1 plus root 3i, goes right here. The real part is 1. The imaginary part is the square root of 3. Like so. Now, the angle in question is right here. This is our standard angle off the horizontal axis. If we draw in this triangle, we see the right side, the opposite side to this angle is the square root of 3, and the adjacent side is 1. And then we're looking for this radius. The radius will be the first thing we can find, pretty straightforward. We get a Pythagorean r squared equals 1 squared plus the square root of 3 squared, which tells us that r equals the square root of 1 plus 3, and the square root of 4 is 2. So our radius is 2. So my complex number z we can write as 2 times e to the, and now we need the angle theta that we'll put in right here before saying times I. So finding theta now. Well, the angle can be found a couple different ways now that we found r, but generally we just, if I didn't have r already, I could still use the given information. We can use a tangent. The tangent of this angle is the square root of 3 over 1. Now, this is actually a standard tangent value. If we're looking at the first quadrant of our unit circle, one thing that can be really helpful to speed up tangent computations is to just memorize the tangents at the primary locations. So the tangent is the y over the x. We have our 3 key points over here. I'll get to the short answer is that the angle is pi over 3, but let's just see why. So this is pi over 6 and pi over 4 and pi over 3. The points are root 3 over 2 comma 1/2, or root 2 over 2 comma root 2 over 2, and 1/2 comma root 3 over 2. Now, if we take the y over the x, that actually gives us the slopes of these lines. And you can do this on your own to confirm, but these slopes should be m equals root 3, m equals 1, and m equals root 3 over 3. Let's see if I can't make that a little bit easier to read. And so if you've memorized your values over here, for the x and y values, then the next thing that would help speed up your computations later on is to just have those slopes memorized as well, and the slopes correspond to the tangent values. We are in the first quadrant for our complex number up here, so we don't have to worry about adding pi or anything. The angle that we have is pi over 3. So we'll go ahead and plug that in for the angle up for our complex number. We've now converted the complex number into its polar form. So if we want the principal square root, we can just say the square root of z equals, actually let's do it as a 1/2 power. So let's do this. Square root of z equals z to the 1/2 power equals this polar form all to the 1/2 power. And we can then distribute that exponent over the multiplication. So we get 2 to the 1/2 times e to the pi over 3I to the 1/2. If you're comfortable with it, I do not mind if you skip this step that I just wrote. May skip. And go times e to the pi over 6I. So our exponent rule that we're using here is when you have, say, x to the a to the b, this equals x to the a times b. So I can just multiply that 1/2 into that exponent. So 1/2 times pi over 3 is pi over 6 times I. We're not distributing here, it's just one multiplication that happens, and that's it. So this is our principal square root in polar form. We want to write this now in standard form. So to convert back to standard form, we recognize that the a value is going to be r times the cosine of the angle, and b equals r times the sine of the angle. I can make this more clear by drawing this picture now, so let's do this. This has a radius of √2 and makes an angle of pi over 6. So we have our real and imaginary axes. Square root of 2 is about 1.3, if I'm remembering correctly. Double check that. 1.4. And we are making an angle of pi over 6. So here's an angle of pi over 6 and a length of square root of 2, and this point right here is the point that we're trying to find. So the a value is going to be the radius times the cosine of the angle, and the b value is r times the sine of the angle. And this just comes from those basic definitions. Cosine of theta equals x over r, or adjacent over hypotenuse. Sine of theta equals y over r, or opposite over hypotenuse. So for this particular example, we get that a value is equal to √2 times the cosine of pi over 6. Just done a little bit more here. And cosine of pi over 6 is √3 over 2. Then our b value is the r times sine of theta is √2 times sine of pi over 6. Sine of pi over 6 is 1/2. And so converting our polar form here back to standard form, we get root 6 over 2 is the real part, and then plus b is root 2 over 2 times I. So now we are back in the standard form of a plus bi. And this is our principal square root. What's interesting here is that there are actually two different roots of our square roots of our initial complex number. And so in the next example, we'll go ahead and see how you can find all of the roots rather than just the principal. And I'll leave this video at that.